Hi guys, today we want to finish off electrochemistry by the calculations. Here you can see electrolysis. There are three parts here I hope to finish, which is part A, state and apply relationship F equals to LE. F is a Faraday constant, is equals to L is Avogadro's number, E is the charge of one electron. So this is actually the charge of 1 mole of electrons, okay? It's Faraday. Okay, so Avogadro constant the charge of electron. And we've done this already, predict the identity of substance liberated. And today we do calculate, the first part we do is calculate the quantity of charge, okay, the total charge, this is the one, okay, which this is the formula you need to know, quantity Q, because I is a current, okay, and then current is ampere per second, so T is time, how many seconds you pass into the electrolysis. So Q is the total charge, okay? The total charge, total coulombs here during electrolysis, okay? And then when you pass this quantity of charge in electrolysis, what are the substances given out? Here, predict the substances given out. And here we talk about the this is the qualitative, this is the quantitative, the mass, solid, and the volume given out here, okay? How much? And also, last part, we determine the Avogadro constant by an electrolyte method, okay? So we go to A, B, C, we're going to start, so A, C, and D, we're going to start C first, okay? So we continue from last week. So a few formulas you need to know. Q equals to IT, Q is the quantity of the total charge used during electrolysis, the total charge, all right? So the charge coulombs. I is the current ampere coulombs per second, total charge, okay? Total time taken in seconds, always in seconds. So you convert hours or days or minutes to seconds, okay? So here, like here, this one is famous, all right? F is Faraday, 1 Faraday constant is the coulombs. L is, E is of course the charge of 1 electron, okay? 1 electron, this is the charge, right? So if I got Avogadro's number of electrons, which is L, right? How many will be, this is LE. This is the total charge can give up 1 more electrons. That's why it's called 1 Faraday, okay? Right, now let's start with this one here. The simple one, let's start first, okay? Let's say in here, in electrolysis of copper sulfate solution, that means the aqueous, okay? A current of 3 amperes. Now, ampere, the ammeter here, you need to know how to draw this diagram. Ammeter here, the voltmeter is put in a parallel. This is in series ammeter, this voltmeter, okay? Voltmeter here, right? Pass through here, and this is a carbon electrode, okay? This is copper sulfate. So this is the I, right? The current I, right, in amperes. So 3 amperes, right, pass for time. This is time, T. Because hours, so 1 hour times, you need to change the seconds times 60 minutes times 60 seconds. Okay, this will be all in seconds now. Okay, so this is the thing. What mass of copper was deposited at the cathode? Now this is the diagram here. This is a cathode. So, and this is anode. So 2 things that are given out, the mass of copper and the volume. So we kill 2 birds with 1 stone, right? So here we go. So first thing, of course, you need to know what is happening here. What are the identities of the things that are discharged, right? We did this last week, or the other one, right? So copper sulfate, remember copper sulfate will contain, there's a copper sulfate here, okay, in ionic form, CO2 plus SO4, 2 minus, right? And water, I told you, right, is H2O, right? Now, of course, in Form 5, you learn that this H2O will ionize, give you H plus. Now, don't use this, but like in this case, you can use it because it doesn't matter, right? Actually, I can show you, okay, like here, right? I put 2 equations here. One is a Form 5 one, and one is a Form 6 one. Okay, Form 6 use water, okay? So these are the ions attracted to this is the cathode, this is the anode, okay? Right, you make sure you know, right? Diagram is here to help you. All right, so of course here CO2 plus will migrate here, and of course, this will happen. It will get the electrons here from the battery here and be deposited as copper. Okay, so this is deposited here. Okay, mass deposited. Okay, so this is the equation here. And of course, in your anode, you got sulfate and water here. So which one is easier to be discharged? Of course, water like we did last week, isn't it? Or the last session. Now you see this one here, this is the A levels one. You can get 2 moles of water give you O2 plus 4H plus 4E. Now in your form 5, you do 4 OH minus to give you 2H2O plus O2 plus 4E. Same as you say 4E here, 4E here. And 1 mole of oxygen here, same as but here use water only lah. Okay, right? Okay, now this equation is important because it will help you to now solve the quantity now at the cathode. Okay, can you see I make it bigger. Okay, right now this is what is happening here is that this is the equation 1 mole here. Okay, this is a 1 mole here. 1 mole of copper 2 plus. Right, with 2, this is actually called 2 moles electron. 2E means 2 moles. We talk in terms of stoichiometry now. 2 means 2 moles now. Here 1 means 1 mole. Here 1 means 1 mole. So 2 moles of electrons, okay, will deposit 1 mole of copper, which means 2:1 ratio. Okay, this is 1 here, sorry. Okay, so now we, and then of course the anode here is this one here. Right, this is the equation here. So we follow this equation now, okay? But you use also can, it doesn't matter because you use 1 mole with 4 moles, 1 mole with 4 moles electrons now. So 1 mole of gas given out plus 4 moles electron, okay? So either way you will use, they don't bother lah. But this one better, okay? Because a lot of questions use this one here. So let's start first, okay? Now, so here, first, of course, we want to find the total current use. Here was IT, 3 amperes, remember? 3 amperes here. We use 3 amperes here. 3 amperes, the current pass through is 3 amperes here. You put here 3 amperes really. Okay, the ring is 3 amperes for 1 hour. So the total amount of charge pass is 3 times 60 because it's 1 hour, 60 minutes. Change it to seconds times, this is the seconds. Okay, so the total 10800 coulombs. Right? So this is the total charge. Now, I want to change it to Faraday, or this is number, can also say number of moles of electrons, also can. Which is, this is the current usage in CIE, okay? So instead of Faraday, it's this number of moles of electrons. But never mind, okay? So this is in coulombs, this is the number of electrons. Now, this one, you use this thing here for both to solve for the cathode and the anode. This is the total number of moles of electron passed through the whole circuit. So here from this equation here, right? This is the equation that's happening at your cathode. So look at 2 moles. 2 moles, okay? You can put now 2 moles of electrons. I say this is the current using, not Faraday, okay? This is the old one, okay? 2 moles of electrons, right? Deposits 1 mole of copper, or 63.5 grams. So therefore, 0.1119 moles of electron will deposit how much? Simple say, this is all simple maths as all. Okay, so this 63.5 over 2 times 0.1119, which is equals to this. So it's the answer. Simple thing. So this is the amount of copper deposited at the cathode. Now for the anode, you use another equation here. This is the one I told you, AS minus A2 minus this equation. So the amount of gas is one here. Normally they always say RTP lah. Okay, they tell you the temperature is 25 degrees centigrade and pressure is 1 atmosphere. So you can use 1 mole of gas occupies what? 24 dm cube. Okay, right? So 1 mole of gas given up by need to be given up by 4 moles of electrons. Okay, so here 4 Faraday or 4 moles of electrons, 4 moles of electrons will liberate 1 mole of oxygen, which is, now here I put 22.4. Depends on the RTP or STP. Here I use STP, 22.4. You can use, if the question says 24, then times 24, yeah. Okay, right? So again, this is how the answer goes. Okay, now this is very simple. Now let's see how we apply this in exams. Huh? Okay, I've got all the things given out here already. Now, this is the first question here. Now this question we did earlier on the electrolysis of brine. Remember not? Okay, you can go back and see lah. All right, this whole thing, first of all, is all on brine electrolysis. Then they tell you, here. All right, starting from here. Sodium chlorate. This one you will learn in your inorganic chemistry. Chlorate 5 is this one here. Okay, why 5? It's a sodium chlorate, sodium ClO3. The whole thing is charged 0. So this one will give you, of course, Na plus ClO3 minus, okay? So whichever way you want to do here, of course, this oxygen is -2. This, of course, +5. Right now. So it's called chlorate 5. Okay, chlorine here is +5. It's prepared commercially by electrolyzing sodium chloride in a cell, which allows the cathode anode to be electrodes to be mixed. All right, the cathode reaction is the same as here, right? Remember 2H2O plus electron given one here, which is this one here. All right, see now. Okay, cathode reaction here, 2 water plus 2 electrons give you here. Right, this is of course what? Reduction. Okay, plus electrons now. Okay, so this is happening in your cathode. I put down here so you can easily see that. And the equation at the anode, remember this is mixed with NaOH, so it's no longer just chlorine plus NaOH and plus OH minus, and this is how you get your chlorate. Okay, so this is a different equation than from the earlier question. So they give you the reaction that's actually happening, right? So this is when chloride mixed with NaOH and oxidized, okay, from -1 to +5 here, okay, right? So you also construct an ionic equation for the overall, which means this one plus this one, these two together, right? Okay, so now I replace them here to make it easier for us. This one I put down here, right? The same thing, Cl minus plus 6 OH minus 6 electrons. You can put the minus over this side plus 6 electrons, or you can, which I normally do because I don't know, it seems more professional though. This one is over here and so forth. Now I'm going to transfer this one to here. Okay, so 2H2O, right? Now, because I want to make the electrons here same, because overall electron, so 6 electrons here, here 2, I times by 3. Okay, now, so times 3, I get 6. 2 and 3 get 6 moles of water. 2 times 3 give you 6 electrons. 2 times 1 here give you 3 moles of hydrogen. And 3 times 3 times 2 will give you 6. So you cancel this. You cancel 6 here. And 3 water, you cancel 6 here, get 3 left. Okay. So come down here, Cl minus plus 3 water, give you this one here. Now this is called the overall equation. Okay. So now see how this kind of question comes out. Okay. Now of course the answer is here. You can see what 1 mole, 3 moles, 1 mole, 3 moles of water. 1 mole. Where is it? Okay. See, 1 mole, 3 moles. Yeah. So this 1 mark here. All right. This is the overall equation. Okay. Now then they say, well, calculate the mass. See, now it's calculation. Calculate the mass of sodium chlorate 5 that is produced when the current so now this is the I pass through the cell for 60 minutes. This is your time. You must change it to 60 times 60, which is in seconds always. Why seconds? Because ampere is what? Coulombs per second. Okay, now, so 1 second gives me 250 coulombs. So you must time 60 times 60 to get the total charge here. This is the total charge. Okay, total charge. Q. Total charge. Okay, right. So you can see Q for IT. This is the total charge. I'm going to put in red color so you can see. Okay, total charge. Right. So 250 is an ampere. 60 minutes times 60 seconds. Okay, so this is 9 times 10 power of 5 coulombs. Okay, so now from the equation here, you can see 6 moles give you 1 mole. Of course, this can be sodium chlorate, can be Na, right? ClO3. Same, isn't it? So 6 moles give you 1 mole. So 6 moles electrons, 6 moles electrons, or 6 Faraday will deposit 1 mole, which is, this is the MR, 106.5 grams of sodium chlorate 5. Therefore, this is the amount of electrons passed. So here you can see I calculate here, right? So this is a total amount of charge. I want to change the number of moles electrons. Now this is very important because I want to use this. I want to tell you, Cambridge now always talk about moles of electrons. There's 2 things, moles electrons and number of electrons. Okay, 2 things here, moles electrons and number of electrons. Number of electrons. These 2 things must tie in to get your Avogadro's number after. So I want to use this method. Okay, so I change these coulombs to electrons, number of moles electrons. So 96500 coulombs is one mole electron. You can see from here. All right, you can see from your data booklet, sorry, here. Okay, on top here. Okay, you can see Faraday constant. Okay, blue color. Faraday constant. All right, F equals to, now this is the value. Okay, which is 965, okay, 40. Okay, right? 965. So this is coulombs per mole. It means coulombs for 1 mole electron. So 1 mole electron has a total charge of this one here. All right? I don't know if I can kill you or not. You Z 1 mole electrons on you. Okay. So here, so 96500 coulombs is 1 mole. So this amount of coulombs have moles. So this 9.33 moles of electrons. Okay. So from here you can see that 6 moles electrons will give up this amount of sodium chlorate 5. So 9.33 moles electrons will give up how much? Simple, 165.5. Now this is how many marks? There are 4 marks here. There's well 3 marks here. See, yeah, okay. So see, they found the number of moles of coulombs, okay, which is Q equals to what? I T. No, 60. Sorry, 250 times 60 times 60. This is 1 mark. Okay, and then they change it. They use number of mole electrons. So change this to number of mole electrons right now. So remember, 96500 coulombs give you 1 mole of electron. So right, so this number of coulombs, which is 9 times 10 to the power of 5, okay? So 9 times 10 to the power of 5 coulombs give you how many? So this or this and this name, 1 mole. 9.33, you can see here 9.33, okay, 1 mark. So this one, 1 mark, it's a 1 mark, okay, 2 marks already. Right, next one, number of moles of sodium chlorate, okay? So you can see here, now how to get this one here? 1.55, quite simple. So remember this one here, right? This 6 moles, yeah, 6 moles. See, 6 moles give you 1 mole, right? Here's 1 mole. So 9.3 to give you 1 over this times this, or 9.33 over 6, number of moles. Okay, I put straight away in mass. So 9.33 over 6. MR, or is a no mark? Sorry. Okay, MR 1 over 6 mark. Okay, and you times this one by MR 1 mark. So total 4 marks. 1, 2, 3, and this one the top man 1, 4. Okay, easy, isn't it? Okay, let's go next one here. All right, now this is on printed circuits. Okay, see an aqueous solution of iron 3 chloride, which is FeCl3. We should actually give it Fe3 plus 3Cl minus. Okay, this fellow here will react with copper, dissolve the excess copper metal in printed circuits. It means Fe3 plus or plus Cu. This one work actually in the first part of the question. I won't bother to go back. Okay, 2 plus your Cu 2 plus. Okay, this one of course will gain electrons. This one will lose 2 electrons. This one from here to here. So minus 2 electrons. This one here from here to here. 2 here, 2 here will gain total of 2 times 1 electron. Okay, so this is the equation 2 here. Okay, you want to, right? This is the overall equation. Okay, right? You can do it up here. All right, you can do this later by yourself. Right, we did it before. Okay, so now is it the resulting solution from dissolving the copper in the printed circuit board was acidified and titrated KMnO4, which means the Fe2 plus here, right, is going to react with your KMnO4. See now? This is done in practical again for AS, isn't it? I know. So 5 Fe2 plus KMnO4, this is the balance for you, so nice. Okay, so remember the mole ratio is 5:1 mole. Okay, right? So the direction is here. So now you're given the molarity of your KMnO4 is 0.02. I put down here already. Okay, volume used is 75.0. So the number of moles of, before you can find number of moles of Fe2 plus, you must find number of moles of KMnO4, or MnO4. So here, number of moles of MnO4 minus Mv over 1000. Of course, you get here, answer is 1.5 and power minus 3. So the ratio is 5:1. So this is the mole ratio within here. So number of moles of iron 2 plus is this one, okay, which is correct. So now look, let's get a marking schema. Okay, so number of moles of KMnO4, 1.5, 10 power 3, which is not here. Okay, or not. Okay, right. And then the moles of iron 2 plus is 7.5. Okay, 7.5, 2 marks. Right, so now the mass of copper that's dissolved in the printed circuit. Remember, this is the equation. 2 Fe3 plus here, from here, right? So you use, they connect all, the whole question is connected. Okay, so here. So again, mole ratio, copper and Fe2 plus. So we have found this one here, number of moles from the titration, right? So remember 1 mole is 2 moles. So how much was the original, sorry, here is some copper, okay? I say copper, not copper 2 plus. Okay, copper. Okay. See. Okay. So it's 1:2 mole ratio. See now. So how much the copper was dissolved? Again, here I know. So this is a mole ratio equation. So bring this up here. Okay, so this is the answer. Right? So it's the number of moles, the answer for the mass. So the times are 63.5, 0.24 grams. See now, 0.24 grams number of moles. Isn't it? So remember, all this will, they will bring in your titration things also to calculate. Now here's another one. Okay, here is electrolysis, right? Because of the increased scarcity and cheaper copper ornaments are no longer made from solid metal copper, but from iron that's been copper plated. Remember now, plating of copper, right? Complete the following diagrams and blah, 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 and blah, blah, blah. Okay, it's quite simple. Okay, so remember here you have the copper plated. Okay, and this, of course, this to be plated, this will be negative one, you know, because copper 2 plus is going to go to, yeah. So it's all electrons here. Okay, this is your positive. Okay, emitter, and so this is your copper also here. So dissolve into here, right? Copper 2 plus. Of course, this is a copper sulfate. This is all from firework, right? So the current passed by is 0.500 ampere. So they want to 3 6 figures pass through the electroplating cell. Calculate the time. Okay, required deposit. Okay, it can be minutes or seconds, up to you. Okay, but of course the answer will be in seconds first. You come to minutes. So here you find the 2 things here. I will put on the 2 things here. First, of course, what's the total amount of the total quantity? Total quantity of charge passed during electrolysis. Okay. right? So Q is IT, I is 0.5, time, well, we want to find the time. So this is the first part. Now, in the second part, the reaction to deposit copper with CO2 plus 2 EDU copper. So from here, I know that 1 mole, right, which is this one here, is 1 mole, is deposited by 2 moles of electrons. 2 moles electrons. Yeah. I use moles, I no longer use Faraday. 2 moles electrons. Okay, remember, Cambridge always use moles now. So for 0.5 grams, how many moles electrons are deposited? Simple, isn't it? It's simple math, isn't it? So it's 0.01575 moles of electrons. Right? So remember this number of moles of electrons. Now, so here, now this is the number of moles of electrons. Now here, the number of moles, can also can find the number of moles of electrons here. Right? So remember, this is the total charge. Right? Remember, now remember, use Faraday constant, okay? Faraday F is equals to 96500. It's called coulombs per mole of electron. Okay, per mole, per mole. Okay, right? So here, right? I know that this is so 1 mole of electron. Or I'd rather put the other way. Sorry, okay. I put simple maths for you now, okay? So 96500 coulombs equivalent to 1 mole electron. Yes, sir. So this amount, and this is your variable here. So 0.5 T coulombs, how many moles of electrons? Right? So 1 over this times not. So it's 0.5 T over 96500. This is the number of moles of electrons required to deposit how much? This quantity. Okay. So remember, this must be equal to this net. So it's the same. Okay. This number of moles of electrons will deposit this amount. So remember this value here, which is here, equals to this value here. Okay. So you can find your T, is it your variable? So T equals to here is in seconds, change to minutes per 60. Now, the marking scheme is wrong, but the final answer correct. So it's 3039.8, okay? Here is wrong, see? Right. But this is correct, okay? So divide by 60, you get 50.66 or 50.7 minutes, okay? So, okay, see the marking scheme, again, number of moles of copper, see number of moles of copper. Okay, here, number of moles of copper. Where is it? Okay, well, you can find from here, see? Okay, so you want, you can put number of moles of copper, follow the method, use 0.5 over 63.5, okay? Right, it's all inside here, but this is already correct already, right? So, okay, it's on here, right? So this whole thing here is marked. So number of coulombs, of course, this one here, Q is IT. Okay, and of course, then you equate it to the time here is 1 mark. Okay, so this is how you do it. So now this one here, of course, is another one here. No, this is the first one we did already, fuel cells. Okay, now, right? I'm trying to make sure we finish on time. Everything inside. Okay, fuel cells, you got hydrogen gas and oxygen gas here. Remember, hydrogen gas, oxygen gas here. Okay, and acid conditions, right? We did this already before. So voltage and so forth, and blah, blah, blah. So here, a fuel cell in an orbiting satellite is required to produce a current of 0.01. Remember, this whole calculation can be for cell and for electrolysis also can. Both can, as long as it involves current, can be used for cell and electrolysis. Okay, now this is a cell. So calculate the mass of hydrogen that will be needed to produce this amount of current for 400 days. So how much weight of actual hydrogen you're going to put into your spacecraft, you know? So remember, this is the equation here. Hydrogen goes to 2 plus, why? Because acid, isn't it? Acid conditions here. See now, this is acid conditions, isn't it? right now. So if acid conditions, this, of course, this is the equation now. Remember, okay, just refer to you again. So don't be idiotic, okay? Okay, so hydrogen is going to produce electrons, which is the current here. So I'm going to put backwards here. H2 give you the one here, which is this one here. So H2, right? So this equation here is a cell reaction, okay? Right? So can see here, right? Okay, this is 1 mole of, right? 1 mole or 2 grams. This 2 moles electron. Always use mole, okay? So 2 moles electrons requires to produce 2 moles electrons for your current, okay? You need 2 grams of hydrogen gas. Okay, so now, so the thing is here, how much is the total charge or total current? Actually, charge is a better word. Total charge is the total charge required. Okay, so time I times T. So remember, they want an ampere of 0.010 times, okay, the time is 400 days, right? 1 day is 24 hours, this is 24. 1 day is, 1 hour is got 60 minutes and change to 60 seconds. So it's a very big, so it's the total amount of charge, this coulombs here. Okay, so remember this, again, I want to find, well, how many number of moles electrons is inside here. Okay, so again, remember that 96500 coulombs is equivalent to 1 mole electron. Okay, so 3, 4, 5, 6, 0, 0 coulombs. How many moles electrons? Very simple. 9, 6. This over this, sorry. This over this times this. 1 over 965 should be, it means 3, 4, 5, 6, 0, 0 divided by 96500, which is on here. Okay, which is 3.58 moles of electrons. Right? So this one here. So remember, so how many moles? So for 3.58 moles of electrons need to be produced, right? By how many grams of hydrogen? So from here, I know that 2 moles electrons is produced by 2 grams of hydrogen. Yeah, from here. Because this is 1 mole. Okay, so I know that from theory, this is from theory. This is theory, theory of the actual reaction happening. So 2 moles electrons requires 2 grams of hydrogen, right? 1 mole, 2 grams in. So many moles of electrons, we 2 over this, 2 over 2 times, okay? So actually it's the same. See now, hydrogen, okay? So this answer here, you can see 3.6 moles, 3.6 grams, okay? Right, hydrogen, yes. So the mark given is the time, you change it to seconds, 1 mark. Yeah, 1 mark. Then total charge, Q is IT. Okay, the whole thing here, 1 mark. 3, 4, 5, 6. See, 1 mark. Okay, these 2 things here got 1 mark already. Of course, then the number of moles is you calculate. So I explained the whole thing here for you because they didn't explain. So this is how you calculate for the number of moles of hydrogen and the number of grams of hydrogen. Okay, right. Let's go on. Next one here. This is on purification of copper. Remember, this is electrolytic purification of copper carried out. Remember, this is your impure copper anode, right? Here we dissolve to CO2 plus. And here, of course, is your anodic sludge. Well, contains, remember, zinc, not zinc, zinc will be dissolved. Silver, gold, whatever, okay? Carbon, oxides, okay, all down here. Okay, so dissolve here, and of course, coming to here will be copper. CO2 plus will go into here. It's copper, right? So impure copper anode contains so forth. We did last week, nickel, zinc, whatever, and so whatever. So remember, they say the copper goes in the solution at the anode, but silver remains a metal and falls at the bottom as a sludge. And zinc also dissolved, don't get. So, and so forth now here. Most of the current pass now, see the current now, the total charge coulombs. Okay, the current, okay, pass through it used to dissolve the copper at the anode. The precipitate pure copper at the cathode. However, a small portion is wasted to dissolve impurities. What are impurities? Like zinc, okay, like what zinc, what else are there also I talked about, okay, right? To dissolve all these further steps. Right, so the current is used to dissolve this one here. They used to convert copper to copper 2 plus. They used to convert zinc to zinc 2 plus. Okay, so wasted. Okay, okay, and so now when a current of 20.0 ampere was passed through a cell for times, so this is your I, and this is your time. You change this to what? 10 times 60 minutes times 60 seconds. So seconds here. It was found that this is the amount of pure copper deposited. Simple, isn't it? This is the mass of copper deposited. So they will guide you step by step. Okay? Remember, they always have most electrons here, most electrons here. Okay. We use blue pen here so that to distinguish them. Okay? So they ask number of moles of copper produced by cathode. Easy then, right? It's of course equals to mass over AR. Okay? So 225 grams over 63.5 is 3.54 moles of copper deposited at the cathode. Marking scheme, okay, 3.5. Okay, 1 mark. All right, so here's 1 mark. All right, take now number of moles. They always go with number of moles. They don't talk about Faraday one. Olden days, Faraday lah. Number of moles electrons produced or needed to produce this copper. So what is the number of moles that the number of moles need to produce on here? So remember now this is the equation. For to deposit copper 2 plus 2 electrons give this. So remember this 2 moles electrons now, 2 moles electrons, and this 1 mole of copper. So right now, so I put down the reverse. 1 mole of copper is produced by 2 moles of electrons. So this number of moles of copper here, so 3.45 moles of copper produced by how much? 201 times, okay? So 7.087. Okay, 7.0. Okay, here. 7 here. Change it to 2 decimal places. Okay, so another 1 mark here. Number of moles electrons given out or required. So 1 mark here. 1 mark here. And number of moles see here. This is the number of moles electrons. Well, what is the actual number? What is the actual? This is the actual. This is only to deposit. This is only to deposit copper. What's the actual number of moles of electron passed through the cell? That means this number of moles of electron passed through the cell also will deposit zinc to zinc 2 plus and so forth. Okay, so number of moles of electrons passed through the cell. It means actually in the circuit. So we can find here. So Q equals IT, the total charge. Total charge. Okay, 20 amperes. Why 20 amperes? See, 20 amperes. Passed for how long? 10 hours. So 10. Okay, 10 times hours into minutes, minutes 60 times seconds. So the whole thing is 7.2, then power of 5, okay, coulombs. Remember again, I told you, to change the number of moles electrons, use Faraday constant, Faraday, with 96500 coulombs per mole electron. Very useful, isn't it? Electrons. So remember, so 96500 coulombs equivalent to 1 mole of electron. So here some other coulombs, 7.2 times 10 to the power of 0.2 times 10 to the power of 5 coulombs, how many electrons? So 1 over 96500 times. You don't know, it's 1 over this not. This over this 100 square or this x. You know how to do that. X over 1 equals to this over this square, whatever. You don't go by the form 3. Okay? And 7.2 times 10 to the power of minus 5 here. So this is the 1 here, right? So 7.461 moles electrons. So here 7.461, right? 46, okay? 1 more. Right? Now here number of moles, sorry, number was coulombs 1 mark, electron. Okay, the whole thing 1 mark. Okay, 7.46 moles electron. Right? So then they ask you last part here. Okay, here. Hence calculate the percentage of current through a cell that has been wasted to dissolve other impurities. So remember, it's always the amount wasted over the total use times 100. This you better know, okay? percentage wasted, actually what is wasted over. Pure means the pure over the total, okay? So this is the one, the total number of moles of electron used. This was the one used to deposit the copper. So this minus this will give the amount of moles of electron that's used to dissolve the zinc or whatever, chromium, whatever, okay? So this one over this one times 100 is 5.01%. See here, okay, 5.01%. See, okay, simple thing. So they use all these methods to solve the whole thing. Now, just for last part, just for sake, okay. Nickel is used to often found in ores with iron. So nickel and iron. So again, here is your nickel plus iron Fe. Okay, remember this is your anode. Okay, right? Anode here, and of course, this is your whatever solution here. Okay, so use okay, after reagent blah blah blah. Use the data in the table to explain why nickel can be purified. Same method. This nickel is going to dissolve inside here. Okay, right? And nickel be deposited at your cathode, the negative in here. Okay, nickel deposited here. Okay, explain why this happened. Of course, now these are the two things here. I quote exactly. Remember in reduction form, isn't it? From nickel here, right? Okay, you can check nickel here. Nickel. Okay, and nickel. See? All right. Quote this exactly. Ni2 plus 2 kiloctane minus 2.5, and of course iron Fe to Fe2 plus, Fe to Fe2 plus. Okay, so not Fe3 plus, okay, so two of them. So which is I quote here, so easier for us to see. So of course, when you undergo oxidation, it go backwards. Here is it. Go backwards, right? So which is to go backwards, which is easier because nickel is positive 0.25. But the way your answer must be E0 for iron is more negative. Okay. So it's what am I doing here? Okay. Yeah. Sorry. What happened? Okay. Here. Okay. Right. Iron is more negative, so iron will dissolve. Okay. No. Right. But no. Yeah. Yes, that's right. Iron is more negative. So remember. The impure nickel copper, the pure nickel copper, and so forth, which means what's left, the Fe2 plus will dissolve, okay? And of course, then nickel will dissolve afterwards, and then nickel will be deposited onto your iron plus, pure nickel here. So because it's more negative, so this one, the reverse occurs, right now. So remember, this is iron will dissolve first, right? Because it's more negative or become more positive reverse. So here it says what? Okay. Remember, iron potential is more negative than so iron will dissolve. Right? Then only nickel will dissolve. And nickel will be deposited onto the cathode. Okay. Now next one, of course, here. All right, now this is a cell here. I'm looking at time. Electrochemical cell was set up on this one here, X2 plus X half cell. They give you this voltage here, which means this is already, this is of course, this is 2 plus 2E, okay? Remember the reduction form, X of course, here is the E standard, it's equals to minus 0.4. They must give this, why? Because otherwise you cannot determine the poles, So silver again is written in the reduction form. Okay, right equation, the equation of the process, okay? Okay, if electrodes were connected, it means this is the overall equation, okay? So remember, this is the arrangement I draw for you already, right? So remember why this is negative? Because this is what? This is more negative now. So your silver will be what? Silver plus electron. You use silver, the E cell will be what? So the E electron will be what? Positive 0.80. So this is positive, this is negative. So negative is your X. Positive is on here. So electron flow from here. So what's the reaction here? X must become oxidation. This is your reduction. So now this is the actual cell reaction here, which means you put this here. Okay. So reaction here is 2Ag plus X gives you 2Ag plus X2 positive. One mark here, you can see it. 1 mark here. All right, see 1 mark here. Okay. So now they ask you now, well, when the current was passed for a period of time, so silver was deposited. That means this one here is deposited. The mass deposited how much is 1.30 grams. Okay. And of course, X lost how much? This one is gain. Is lost. How much is lost? Well, 0.67. So of course this is lost. So of course then you calculate lah, right? So number of moles lost will be of course n number of moles lost is equals to n equals to m over AR. So you want to find the AR, so calculate the AR for metal. Suggest the identity. So over AR. So I don't know. So 0.67 over AR. Okay, now silver gain will be of course 1.30 over the AR for silver, which is 1 over 7.9. Okay, so it's the number of moles of silver. Okay, so remember now the ratio 1 mole is to 2 moles. That's all. Okay, so the number of moles of this one here, X over number of moles of silver is 1 to 2. Okay, so I just substitute this one inside here. So number of moles, I bring this up here. So this one here, and I just put this down here. Right, so I can just cross multiply. And I found that my AR is 111.2, which is checked from the data booklet, is cadmium. Okay, so this is how it comes out in exams. Okay, now, so the whole thing is 4 marks. 4 marks, man, my goodness, 1, 2, 3, 4. 4 marks here. Number of moles of silver, no moles of X, 2 moles here. 2 moles, from here is it, 2 moles, 1 mole, and number of moles lost and so forth here. Moles gain, moles lost, and then the AR. 4 marks. Okay, now, next, of course, is to find Avogadro's number, which is here. You can see I've gone through a bit fast, right? So we're going to talk about some determining a value for Avogadro's constant, which is L is equals to 6.02 10 to the power of 23 by a electrolytic method, means by a experiment. This one come up for paper 5 as well as for paper 4. So better know how to do this. Okay, now let's see how they are asked here. Right, now the apparatus, if a cell is determine Avogadro's constant. Okay, so power supply is a resist. This variable resistor, of course, is called what? Called a rheostat. Okay, rheostat. Okay, this of course is an emitter. They put X here. See, you need no emitter because it's in series, isn't it? If like that, it means it's a voltmeter. Okay. Suitable electrolyte, of course, if it's silver here, it's silver nitrate. Because it's Ag plus, silver nitrate, or whatever, anything that is soluble, silver soluble salt. Okay. So they say, well, in experiment, the current of 0.2 amperes or so, of course, is your I. Pass through 40 minutes is your T times, if T equals to 40 times 60. Remember, always change your seconds first. The mass deposited is this one here. Oh, fantastic. Now, they normally lead you, which is very good. All right. So remember, they tell the charge of electron is this one here. Because you should know how to use it because it's here. Okay, it's in your data booklet. If you don't know this, you will fail. Okay, here. Okay, it's given here. All right. See the charge. I'm going to rub it off first. Okay, here. See. No rubbish. Okay, I use blue. See, electronic charge. Okay, this is 1 electron. That means 1 electron, the number 1. Okay, 1, 2, 3, 1 electron, 1 electron, 1 electron. See, 1 electron and 1 more electron, the difference, eh? 1 electron is just 1. 1 more is 6.02 10 to the power of 23. No, 1 electron. 1 electron carries this charge, very small charge. You won't die lah. Just throw 1 electron at you. Okay, so this is the charge here. You can see here. Okay, just that they give it to you. I don't think they should give it to you. They should do it yourself. Okay, it's for on the electron, on 1 electron. Okay, right. So calculate the number of moles of silver deposited. Very simple. N equals to M over AR. Okay, this is number of moles. Okay, very simple. Number of moles electron, number of mole coulombs. Coulombs, that means the total charge. Q is IT, 0.2, 0.2 amperes, and time 40 times 60. So it's the number of coulombs. So they again I said number of electrons. See, number of electrons, not number of moles. Number of electrons, right? Number of electrons here, right? So remember, this is coulombs. So remember here. Now remember, you're supposed to find Avogadro's number now, right? So this is another way of doing things. Normally we use 96500 coulombs equals to 1 mole. Okay, right now. So now cannot, because I want to find something here. So I use another way. I use here. How many electrons are there? I want from here. I want to find how many electrons are there. Okay, to give me 480 coulombs of charge. See now, how many? Okay, so I know that a charge of 1.6 minus 9 coulombs, one electron. 1 electron, not 1 mole, 1 electron. So this number of coulombs, how many electrons? So this is the number of electrons. Quite a lot, isn't it? Right? So this number of electrons, this is the total number of electrons, right? Okay, that will deposit this number of moles of silver. Okay, so I connect this one with this one here. Okay, right? Okay, now they ask 1 mole of silver, isn't it? So this is mole of silver. So I know that this one here, 0.00463 moles of silver need this number of electrons. Number of electrons, not number of moles, number of electrons, right? Remember now. Okay, so 1 mole of silver requires how many electrons? So this number. So 6.4, blah, blah, blah. This is Avogadro's number, isn't it? Because Avogadro's number is one mole, right now. Is Avogadro's number what? Avogadro's number. So 1 mole of silver requires this number of electrons, which is actually Avogadro's number. See not? Okay. So answer is here. Okay. Right. This is the answer. Right. Here marking scheme. Marking scheme here. Okay. Yeah, here. Okay. So here we can see time. I want to finish off. Okay, see now, 6 point, okay, can see the whole thing now, okay, step by step, can all right, go back and review it. Okay, now here another question here, an oxide of iron was dissolved in inert solvent and electrolyzed for 2 hours. So here's time again, 2 times 60 hours, 2 times 1 hour 60 minutes times 60 seconds, okay? So this is I current. Electrolysis products are iron and oxygen. Okay, that means iron. That means this must be the equation because it says here the mass of iron is 1.11. See the iron here, they didn't tell you what kind of iron is it. Calculate the oxygen number in the oxide. Normally it's +2 or +3 but you don't know. So I put X plus, okay, right, or plus X. But normally it's X plus, okay, up there, right? So put X plus here. I'll take a bit more time today. I want to finish off. Okay, this is X plus, okay? So 1 mole, I'm going to put blue, so easier to distinguish when you read over. So 1 mole requires X moles of electrons. To give 1 mole of iron, this is your solid, no, solid. Is a metal. Okay, so number of moles of iron will be how much was deposited? 1.11. Okay, over AR, this is AR, guys, 55.8. So the number of moles of iron deposited. I know this from here. So the total number of current charge is equal to IT, so 0.8 ampere times 2 hours times 60 times 60. Okay, so this is the total coulombs. Right? So now can I find the number of moles of electrons now? Okay, number, see, number of moles is the number of moles. Number, not number of electrons, no, number of moles of electrons. Okay, remember, I told you already, right? 9650. Now you can use Avogadro's number here because they didn't say find Avogadro's number. Okay, coulombs, right? 65 coulombs, okay, equal to 1 mole electron. Okay, so that means this number of coulombs, 5760 coulombs, how many? Right? So 1 over 96500 times your 5760 is here. So it's the number of moles of electrons. So this number of moles of electrons have deposited this number of moles of iron. So I connect here. So so I connect this one to this one here. 0.0119 moles of ions deposited by these moles of electrons. Yeah. Okay. So 1 mole of iron deposited how much? This is what this one. So it means I need 3 moles of electrons. It means it must be plus 3 moles of electrons. So 1 mole is to 3 moles. So 3 means this one's 3 then. Right? To give me 1 mole of Fe. Okay. So it's 3 plus. See the marking scheme? Okay. So here the whole thing is 1 mark. Number of moles of this one is 1 mark. Now next one. All right. H2SO4. Okay, this is quite simple. I think you do it yourself. I want to go to this current Avogadro's number. Okay, here we are. I did one with you already. Here, this is the one we did. Okay, right. So here, if the charge of the electron, the charge electron of that means 1 electron. 1 electron. What's the charge? 1 minus 1.6 times 10 to the power of minus 19. Okay, right? The AR valency of copper is known. That means I know this. Okay, the value of Avogadro's number can be determined experimentally. This is the whole thing. It's done by passing a known current for a known time through the copper electrolysis weighing, so forth. Okay, so draw the diagram now. I just want to go quickly here. Okay, a power supply. Okay, long, short, emitter, right? Anode, cathode here. Okay, this anode will be, can put copper lah. This is copper again. Okay, right? Allow this one or this one again. Okay, so right now is it 4 marks? No, just drawing here. Copper sulfate, anode. Okay, inwards, right? You must put inwards. Okay, 1 mark each. So now. So they say here, the following results are obtained from such an experiment. Okay, current pass through the cell is this one here, time pass is this one here, and the mass initial final means that this minus this will be the mass of copper deposited not, okay, which is 52.542 minus 52.243, right? Okay, it's here. So first, of course, remember, 2 things you must remember for Avogadro's number. You need to find the number of moles of electrons and number of electrons. How many? 1, 2, 3, 4, 5. Okay, 2 things here. So I put 2 things separate here. So first of all, I find the number of moles electrons to deposit this copper. So number of moles of copper is this one here. Remember, this one minus 1 here over 63.5. This is the number of moles of copper deposited. Okay, now. Yep. So now I want to find the number of moles of electrons. I know that from theory, this is the equation, right? So 1 mole of copper here is deposited by how much? 2 moles of electrons. Okay. So 1 mole of copper deposited by 2 moles of electrons. So for this number of moles of copper, how many moles of electrons? So here, this is so this all this time, this one. Okay. Right? This is the number of moles of electrons. Okay. Number of moles of electrons to deposit what? To deposit this number of moles of copper. Now, then from the current, I found that for Q, total amount of charge passed through it, Q is of IT. So what is the ampere use? 0.5 here. 30 minutes times 60, so it's 900 coulombs here. Okay, now I'll find the number of electrons. Number of electrons that are producing something here. Okay, so remember, 1 electron produced by 1.6 times minus 19 coulombs. So 900 coulombs will be this all this number. Okay, so that is the number of electrons. Now this number of electrons here, remember, this number of electrons here is produced by, right? this number of moles of electrons, you know. See here is moles electrons is the number of electrons. So now I'm going to equate these two here, these two together into here. So 9.42 times 10 power minus 3 moles electrons is equivalent to this number of moles, this number of electrons. So 1 mole electron, oh, of course, give me our number lah. That's 1 mole electron lah. See? Okay, let's see. All right. So here it says here, calculate first number of moles of copper. Okay, and then number of moles of electron. See, 2 marks here. Number of moles of copper, right? Moles of copper, 1 mark. Number of moles of electrons, 1 mark. Okay, so then they see the marking scheme is very important. No. Okay, the total amount of current passed through is Q equals IT. No, sorry, Q equals IT. I'm going to hurry up. Okay, here, right? So number of electrons is right here. Okay, so these two you to relate it, you get the answer here. Okay, all right. Now for last one, it's the same thing here. Same thing one. Okay, now here they ask you for the relation of F Faraday constant Avogadro number. Remember, Faraday is the amount of current for 1 mole. This E is for 1 electron. This is for 1 mole. Which is 6.02 10 to the power of 23. Okay, so this one here, LE here, F equals to LE. Okay, a current of 1.2 ampere was passed through the sulfuric acid for 30 minutes and so forth, and this is the oxygen given out, so forth. Yeah. Now this is given here direction here. Now remember, they use water here. So 4 moles of electrons, 1 mole of oxygen. Remember this? So they use this data and the data booklet to calculate the Avogadro's constant L. Okay, and so forth. Now step by step, they do it very simple. Okay, so number of moles of oxygen produced, easy. Right now, the V over your, okay, over the, now of course here they say this RTP lah. No, 25 atmosphere. So over 2400, this will give the number of moles of O2. I'm going to use red pen now just to do this to efficient myself. Now, number of moles electron required. Remember here, how do I get this one here? 1 mole requires 4 moles from here. So now, 1 mole of oxygen requires 4 moles of electrons. Okay, remember? So 1 mole of oxygen requires 4 moles of electrons. So how many moles of oxygen was produced? This one here, from here. Okay, so it requires this number of moles of electrons. Okay, okay. So now I need to find the number of moles or a number of electrons today. So then it says number of moles of the number of coulomb used. Okay, Q is IT, 1.2 ampere, right? Here 1.2. Okay, 30 minutes. 30 minutes. Here 30 minutes. All right. Here 30 minutes times 60 seconds. Okay, so this is the coulombs, total amount of coulombs. So in this coulombs here is produced by how many electrons? There I use my charge now. Okay, so this 1 electron carries this amount of charge. So 2160 carries how many number? Carries this number. So now these two I must relate now. The moles and the number. Okay, so this number of moles, right? The number of moles electron is produced by how many electrons? This number. So I put down here. See now, 2.17 number of moles of the electrons contains, right? Okay, produced by or contains this number of moles, number of electrons. So 1 mole of Avogadro's number. Okay, so here the marking scheme, 1 mark each. Okay, so I finished electrochemistry already. So go over it again and then you can see that. Okay, so goodbye and please go over and make sure, because this is I finished electrochemistry. Yeah, the next time I'll start, of course, ionic equilibria. Okay, so we're gonna stop recording.